Vacuum systems are used extensively in semiconductor manufacturing. Therefore, in this video, we'll provide an overview of vacuum systems. Using two examples, we'll explain the reasons for utilizing vacuum systems in semiconductor manufacturing. We will then provide an overview of the vacuum principles. The ambient air contains several gas molecules. This includes nitrogen, oxygen, carbon dioxide, and argon. The presence of these molecules often degrades semiconductor processes. Let us illustrate the detrimental effects of ambient gas molecules using two examples. The ambient gas molecules can unintentionally incorporate into the materials during fabrication processes. As we explained in an earlier video, the source and drain of a transistor can consist of silicon germanium pockets. These silicon germanium regions are grown using a process called chemical vapor deposition technique. The presence of oxygen during the chemical vapor deposition process can promote the generation of structural defects and degrade the crystal quality of silicon germanium in the source and drain regions of the transistor. Let us now look at another example. Some materials such as titanium are highly reactive in that they can interact with oxygen and carbon. Here is a cross-sectional transmission electron microscopy elemental analysis of a graphene device showing that the deposited titanium contact to graphene is not pure. It intentionally incorporates both oxygen and carbon. These two examples highlight the detrimental role of residual gas molecules in semiconductor manufacturing and fabrication of the electronic devices. Therefore, these examples lead to an important question: how to remove these residual gases during the fabrication process. A dominant and effective approach for reducing the concentration of gas molecules is through the evacuation of the spaces in which the fabrication process occurs. The term vacuum refers to a given space filled with gas molecules at pressure below atmospheric pressure. This means having a density of gas molecules less than 2.5 times 10 to the power 19 molecules per centimeter cube. Vacuum is generally achieved by pumping on a vessel. It is important to highlight, as we'll see in this video, that even at the lowest vacuum levels attainable by existing technologies, there are still residual molecules inside the evacuated space. This discussion brings us to the question of how to quantify vacuum levels. To quantify the vacuum levels, we will need to familiarize ourselves with three concepts. These concepts are molecular density, mean free path, and time to form a monolayer. Molecular density is the average number of molecules per unit volume. The mean free path refers to the average distance that a molecule travels in a gas between two successive collisions with other molecules of that gas. And time to form a monolayer refers to the time required for a surface to be covered by a layer of the gas of one molecule thickness. Furthermore, the vacuum quality is classified into three main categories according to the pressure of the evacuated chamber. These are low to medium vacuum, high vacuum, HV, and ultra-high vacuum, or UHV. The low to medium vacuum ranges from the atmospheric pressure to about 10 millitorr. The high vacuum ranges from 1 millitorr to about 10 to the power minus 7 torr. In this regime, the mean free path of residual gas molecules is equal or greater than the dimensions of the enclosure. Finally, the ultra-high vacuum, or UHV, ranges from 10 to the power minus 7 torr to 10 to the power minus 16 torr. In this regime, the time to form a monolayer is equal to or greater than the usual time required for laboratory measurements. We now use these basic concepts to quantify the vacuum levels. The plot here shows how molecular density, mean free path, and monolayer formation time evolves as a function of the vacuum pressure. This is a relatively busy plot. To help explain the plot here, let us familiarize ourselves with the different axes of the plot. The y-axis on the left-hand side represents the molecular density in units of molecules per centimeter cube. On the right-hand side, we have the monolayer formation time in units of seconds and mean free path in units of centimeter. The plot here also marks the different categories of vacuum from low to medium vacuum, high vacuum range, and ultra high vacuum range. As we can see in this plot, as the pressure decreases from the low pressure to ultra high vacuum pressure, the molecular density decreases. Simultaneously, the reduction of the pressure leads to the increase of both mean free path as well as the improvement of the monolayer formation time. Let us consider two pressure levels and examine their effects on molecular density, mean free path, and the time to form a monolayer. At a low vacuum of about 10 millitorr, the molecular density is in the range of 10 to the power 15 molecules per centimeter cube. This is a very large density. As a result, it increases the likelihood of collisions between the molecules, resulting in a low mean free path of about 1 centimeter. Furthermore, this coincides with a small monolayer formation time of 100 microseconds, in that in this vacuum it takes only about 100 microseconds to form a monolayer of residual gas on the surface of the wafers. In contrast, when the vacuum level improves from 100 millitorr to about 10 to the power minus 10 torr, which falls in the ultra-high vacuum regime, the molecular density drastically decreases by almost about 9 orders of magnitude. This results in the improvement of the mean free path to about 10 to the power 8 centimeters, as well as the improvement of the monolayer formation time to about 10 hours. This discussion illustrates the importance of increasing the vacuum pressure in device fabrication. As we'll explain in a later video, achieving high and ultra-high vacuum levels require several pumping systems. Let us now review some of the applications of the vacuum systems in semiconductor manufacturing. The high vacuum is typically used for vapor deposition systems, such as evaporation and sputtering. The ultra-high vacuum, or UHV, are used predominantly for material synthesis in research settings. Examples of such systems include molecular beam epitaxy and ultra-high vacuum chemical vapor deposition systems that are used for epitaxial growth of semiconductors such as compound semiconductors and silicon germanium. Now that we know the significance of vacuum systems, it brings us to the question of how to generate vacuum. The equipment to generate a vacuum is called vacuum pump. Various vacuum pumping mechanisms exist which provide different pumping capabilities, as illustrated in the graph on the right-hand side. X-axis of this graph shows the pressure of the vacuum chamber ranging from the atmospheric pressure to ultra-high vacuum levels. Depending on the vacuum level requirements, different pumping systems can be employed. For example, the rotary pumps can accomplish low to medium vacuum levels. On the other hand, molecular and the cryogenic pumping systems can achieve high vacuum and ultra high vacuum levels. Indeed, in practice, high vacuum and ultra high vacuum levels are achieved by initially using a rotary, for example, a rotary pump, followed by implementing and employing a molecular or cryogenic pump. In the next video, we'll discuss the different types of vacuum pumps that are commonly used in semiconductor fabrication systems. Specifically, we'll review the operating mechanisms of scroll pumps, turbomolecular pumps, and cryopumps.